In this section, we're going to be looking at some more properties of logarithms. So what I think I'll do in this video is I'll just talk about each of the rules that you're going to look at in this set of notes and give a small example for each. In the examples for this set of notes, you'll see many more complicated examples, but I just want to give you sort of a basic sample of what each of these rules can be used for. So the first property that we're going to be looking at is the inverse property for the logarithm. That's just the defining property for a logarithm. So remember that we defined the logarithm to be the inverse function to its corresponding exponential. So recall that ln, it means the natural logarithm. So that's our abbreviation for log base e. And that means that that function should be the inverse function to exponentiation with base e. And what we've seen is that if you plug in one inverse function into another, or really I should say one function into its inverse, then these are cancellative and you'll end up with just the original input x. And this cancellation works in either direction. So if you plug in the exponential function into its logarithm, then you get x. And similarly, if you plug in the logarithm into its corresponding exponential function, then these are again cancellative and you'll get x. So these are called the inverse properties for logarithms. Now these work for any base. So here I've chosen to look at the natural base, but you could also have rules like log base 10 of 10 to the x is equal to x, for example. Same idea, you're just plugging in an exponential function into its corresponding logarithm, and this logarithm was defined to be the inverse to this exponential function. So they'll cancel out and you'll end up just getting that exponent there. You can use this to evaluate certain logarithms if you want to. For example, if I gave you log base 2 of 8, if I wanted to use the inverse property to compute this logarithm, then I would want the inside of this logarithm to be a power of 2, which thankfully it is, so I can write it as 2 cubed. And now I have log base 2 of 2 to the something. We know that log base 2 of 2 to the x would be cancellative, and we would just get that x. So in this case, these will cancel and leave us with just 3. So log base 2 of 8 is equal to 3. So that gives us a way of simplifying the logarithms by trying to make sure that the inside is written as an exponential term with base 2, and the outside is that corresponding logarithm with base 2. You basically just want these to match. You want the base of the logarithm and then the base for the exponent on the inside to match. And then you can use this cancellative inverse property. Now notice that, just to remind you, this logarithm can be interpreted as an exponent here. Remember that our reading for the logarithm was like this. You can think of this expression as asking, what exponent would I put on a 2 to get an 8? And the exponent that you would put on a 2 to get an 8 would be a 3. So you can read logarithms in this way because they're essentially just inverting exponentiation with base 2. So you can think of this either way. You can either read it as what exponent would I put on a 2 to get an 8, or you can use this cancellative property that I did here. Either way, you should end up getting 3 as your answer for this one. The next rule that we're going to look at is new for this section. So we're going to look at the product rule. So before I actually write down the rule, let me try to explain where these rules are coming from. Basically, because the logarithm is an inverse to exponentiation, we can use any property that we know about for exponentiation and convert it into a corresponding property for logarithms. So for example, if you wanted to derive the product rule, we know that if you have addition of two exponents, then that corresponds to multiplication on the outside of the exponential function. So in other words, the exponential function is going to take addition on the inside and turn it into multiplication on the outside. Or said another way, addition of arguments for the exponential function will turn into multiplication of the exponential function for those two arguments. Now, you can reverse this rule for logarithms. So logarithms will do the opposite. If you have multiplication on the inside of a logarithm, then it will turn into addition on the outside of a logarithm. So it looks like this. So this is called the product rule for logarithms. It says that if you're multiplying two things on the inside of a logarithm, then you can convert that into a corresponding sum of the logarithms of each of the individual factors. So I'm not going to write down the justification for the remaining rules that we're going to look at, but each of these rules is coming from some corresponding rule that applies to these exponents. So this is our product rule. This can still be used to simplify expressions. We're going to make better use of this rule whenever it comes to solving logarithmic and exponential equations in the next section. But for now, let's just see an example where you can use this to simplify an expression. Let's say that you have log base 6 of 3 plus log base 6 of 2, and you wanted to simplify this. Well, if you were trying to use the inverse property that we had up above, we might be stuck, because notice that neither 3 nor 2 are powers of 6. At least they're not convenient powers of 6. So it doesn't look like we'll be able to simplify this much, but I can combine these into a single logarithm using the product rule up here. So I know that if you have ln of something plus ln of something else, I can combine those into a single logarithm, which is ln of their product. And this works for any particular base. So here I'm working with log base 6. I can combine these into a single log base 6 of the product between 3 and 2, which would be 6. So this is the same as log base 6 of 6. The type of logarithm is not going to change on either side of this equation. So if you started with ln's, the combined logarithm will be an ln. And similarly here, we started with 2 log base 6's, so their combined logarithm will be a log base 6 of the product of the arguments. And lastly, to answer this, you can say, what exponent would I put on a 6 to get a 6? The exponent that I would put on a 6 to get a 6 is a 1. Or if you wanted to use that inverse property, I can think of this inside as being a 6 to the first power, and then I can cancel to get a 1. Remember here that this cancellation is not like a multiplicative cancellation. It's not that I'm dividing by a logarithm. It's that I'm applying one inverse function to another. And therefore, by the inverse property, I can cancel out this inverse function with its inverse. Okay, so next let's look at another rule. This is the quotient rule. The quotient rule is true for similar reasons. I'm again just going to state it for the natural logarithm, but this is true for any logarithmic base. Now here, if you have division of two things on the inside of a logarithm, they actually turn into subtraction on the outside of the logarithms. So if you have ln of x over y, you can write this as ln of the numerator minus ln of the denominator. So you can split ln of a quotient into two separate logarithms. And this again can be useful whenever you're trying to simplify some expressions. For example, let's say that you wanted to evaluate log base 2 of 12 minus log base 2 of 3. Again, neither 12 nor 3 are convenient powers of 2, so I wouldn't be able to immediately simplify this, but I could use this rule to condense these two logarithms into a single logarithm. I could write this as log base 2 of, because I have a difference of logarithms on the left side, I should get a quotient of their arguments on the inside based on this quotient rule. So I can take the two logarithms that I started with on the left side and convert them into a single logarithm. That would be log base 2 of 12 over 3. So I divide the arguments. That would be log base 2 of 4. And see if you can simplify this on your own without me telling you what this should be. So this should be a whole number. What is it? It might help to rewrite the inside as an explicit power of 2 so that you can cancel. But in any case, the point is that the power that you would put on a 2 to get a 4 is a 2. So the answer is 2. So that allowed us to simplify the expression that we started with over here. Next, we're going to look at the power rule. The power rule is one of the most useful that comes up with logarithms. And again, this works for any logarithm, but I'm just going to state it for the natural logarithm. So if you have log of x to a power, or log of anything to a power, you can take that power and you can set it on the outside of the logarithm as a multiplicative factor. So this is the same thing as m times ln of x. So you can bring that power down and set it in front of the logarithm. So this is mainly useful whenever we start solving these equations involving logarithms. For example, if we had an ln of x squared and we wanted to be able to solve for x, we don't like the fact that there's an x squared here, but I can rewrite this using the power rule as a 2 times ln x, and that's made it a little bit easier for us to isolate x. Now we can't go any further in this example because I've just simplified the expression, but in the next section we'll talk about how to solve logarithmic equations, and then we'll be using the power rule a lot. So the convenient thing is that you can just take any exponent that sits on the inside of a logarithm and you can bring it to the outside like this. The same rule works in reverse, so if I had something like 3 times ln of x plus 1, I could rewrite this as ln of x plus 1 cubed, so I could bring the power to the inside. But notice that the entire argument for the logarithm inherits that power. So this x plus 1, the entire thing, should be cubed if you bring one of these multiplicative factors to the inside of a logarithm, like this. So you'll see in the next section a few more uses of the power rule, but that's all I want to say about it for now. And then there's one last rule that we'll see in this section, which is called the change of base formula. This one is not going to be as useful when it comes to solving logarithmic equations, but it is useful if you rely on your calculator a lot. So if you plan on using a calculator to get decimal approximations to a lot of things, then this one will be useful to you. What it says is that if you have log base b of something, you can convert that expression into a log with a different base if you want. So you could write this as log base a of x divided by log base a of the original base for any value of a that you want. So this allows you to take something that's written in an inconvenient base and exchange it for an expression that's written in a more convenient base. So for example, let's say that I wanted to know what log base 3 of 7 was as a decimal. Now, I might not know how to plug this into a calculator. So that's kind of inconvenient. If I just have a scientific calculator, I don't have a log base 3 button. But what I can do is I can try converting this expression into a more convenient base, like the natural base, because I do have an ln button. So this would be converted to ln of 7 divided by ln of the original base. And this right-hand side is something that I could plug into a calculator. And then I could just plug it in to get whatever decimal approximation I want. So the change of base formula is mostly useful for things like this, because it allows you to come up with decimal answers for these original expressions. But in the next section, we're mostly going to be focused on the rules that preceded this, because the power rule, the quotient rule, the product rule, those are going to be a little more useful when it comes to solving exponential and logarithmic equations.